All right, this entire chapter is about probability and counting theorems. We're going to start with the fundamental counting principle. And what that says is that we can figure out how many different ways, if we have more than one event, how many different ways they can occur together. So in number one, they ask us to find the number of ways all of the events can occur. So in one, we have two events. In event one, we only have three ways that it can happen. We have three options there. In event two, we have seven options, seven ways that event two can play out. So if we multiply 3 times 7, we see that we have 21 ways that both of those events can occur if we were to combine them. Okay. If you have more than two events, like in number 3, we have event 1, 2, and 3, then you do the same thing. You just take the number of ways for each event and you multiply those together. So 4 events in the 4 ways in the first event, 2 in the second, 9 in the third will give us a total of 72 possibilities for how these two can play out. These three, can play out together. Now we can take the same idea and answer number 5. It says, for the given configuration, determine how many different computer passwords are possible if, and they're going to give us two scenarios. In scenario A, the digits and the letters can be repeated. In scenario B, the digits and letters cannot be repeated. So once you choose a digit, you can't choose it again. So if we have a password that has to be 3 digits long, and then that needs to be followed by 4 letters, we have to think about how many digits we have to choose from. So we're talking about digits, not numbers. It has to be a single place digit. So that would be 0 through 9 would be our options. So we have 10 digits to pick from for our first number in our password. Then we go to the second number in our password. Because we can repeat digits, we still have 10 possibilities. Same thing for the third digit. Okay, no, so this is going to be scenario A, but watch, scenario B says we cannot repeat digits. So that means the very first digit we have 10 to choose from. 0 through 9, we're going to pick one. Once we've picked one of those, though, we can't pick it again. So for the second digit in the password, we only have 9 options. Once we've picked that, that's no longer available. So for that last and third digit, we only have 8 options. So that's how this changes depending on whether you can repeat or not. All right, then let's go back up to scenario A. We have 4 letters that we have to pick. We can repeat them in scenario A. So there are 26 letters in the alphabet. Every time we have to choose a letter, we have 26 options. But down here in scenario B, we cannot repeat. So once we have picked a letter, that first letter we can pick from any of the 26, but then that second letter, we only have the option of 25 options. After we've done that, we only have 24 options because we can't repeat. And then again, for that final and fourth letter, we only have 23 possibilities. So when we plug these into the calculator, and this one up here, letter A, we can really plug it in as 10 to the third times 26 to the fourth. We could do that. So 10 to the third times 26 to the fourth. If that's easier for you, that comes out to be 456,976,000 possible passwords. All right, so that's with the option of repeating digits and letters. If you cannot repeat digits and letters, then we end up with almost half less, 258,336,000. So those are the number of passwords that are possible given these constraints. All right, we can try one more. Let's try number 2 here. I'm sorry, number 6 here, and I'm going to write it out here to the side. So again, we have 2 scenarios. A, where we can repeat, and B, where we cannot repeat. So only 2 digits this time. So the first digit, we have 10 options. Second digit in scenario B, in scenario A, we also have 10 options. Scenario B, 10 options for the first one, but only 9 for the second one because we're not going to be able to repeat whatever we chose in that first slot. And now we have 5 letters. So this is going to end up being 26 5 times, right? Since we are able to repeat, so I'm just going to say 26 to the 5th. This one, however, I'm going to have to say 26, then 25, then 24, then 23, and last we have 22 options. So letter A scenario with the repetition gives us over 1 billion password possibilities. Without the repetition, we end up with 710,000, a little over that. Now moving down to number 9, you see something new that we haven't seen before, and that's this exclamation point. The way we read that is factorial. So 5 factorial, what that means is that I'm going to multiply together every number starting with 5 as I count down to 1. So I'm going to multiply 5 times 4 times 3 times 2, and then finally times 1. All right, when I multiply all of those out, I get 20 times 3 is 60 times 2 is 120. So 5 factorial is 120. 10 factorial, we do the same thing. We start with a 10 and we count down till we get to 1. And we're multiplying all of those together. So if I multiply 10 times 9 times 8 times 7, of course I'm going to use a calculator for this. I'm going to end up with 3,628,800. Now on number 13, a problem like this, I need to find 3 factorial before I multiply it by that 5. So for example, I'm not distributing the 5 in because then that would be 15 factorial. When really and truly what's inside the parentheses is 3 factorial, which means 3 times 2 times 1. I'm going to get a very different answer for that. That will be 6 from the parentheses times that 5 will give me 30. If I did 15 factorial, I would get a very, very large number. So make sure you follow your order of operations. I mean, even though we're not writing 3 times 2 times 1 in the parentheses, that's what's in there, and you know you have to take care of parentheses before you do anything else, according to your order of operations. All right, same thing here with number 14. This is 4 factorial times 6 factorial. So I'm saying this isn't 24 factorial, it's 4 times 3 times 2 times 1 times 6 times 5 times 4 times 3, and so on. All right, and then when you go to put that in the calculator, of course you could put it in is 6 times 4 raised to the second power. Oh, I forgot the 5. The 5 needs to be in there as well. 3 raised to the second power. And then 2 raised to the second power. And of course 1 raised to the second power. I'm just going to leave that out since that would just be 1 itself. So make sure you're following order of operation when you do these. And 16 over here, that would be 6 plus 2, so that would be 8 before I take the factorial. So that would be 8 factorial. All right, you might think that you would distribute that factorial into the parentheses, but that would go out of order of operation and would give you a different answer. All right, so moving to the back of the sheet, we have what's called permutations. And permutations are just the way in which a certain situation can happen, a number of ways in which it can happen. And so the formula for permutations is written like this. All right. And what we need to know is what the N and the R stand for. So the P stands for permutation. So that's the number of ways, the number of combinations. This N stands for the total number of objects. So this is the total objects that we're going to be selecting from. R is the number of objects that get selected together. Okay, so in our 17 here, we can see that the N is 4, the R is 3. So that means that out of 4 objects, we're going to select 3 at a time. And so what we do is we take the N, we just follow this formula here. We take the N and plug that in the numerator as 4 factorial. And then in the denominator, we have 4 take away 3. That's just what the formula says, 4 take away 3 factorial. So we're going to have to do the subtraction before we do anything else. So we end up with 4 factorial over 1 factorial. So 4 factorial is 4 times 3 times 2 times 1. And all of that is going to be over 1. 1 factorial is just 1 itself. So we can really kind of disregard that denominator altogether. So that will give us 24 permutations when we have a situation where we have 4 objects and we're going to select 3 at a time. We have 24 ways that could happen. Right? If we look at number 21, in this case we have 10 objects. We're going to select 3 at a time. So we follow the formula. 10 factorial goes on the top. And then 10 minus 3 factorial will give us 7 factorial on the bottom. All right, so in the numerator would be 10 times 9 times 8 times 7, etc. In the bottom would be, we'd do the same thing, only we're going to have 7. All right, so 10 times 9 times 8. I'll show you here how we can make this a little bit easier. Oh, that's supposed to be 4 times 3. And that's all going to be over. So now we have a division problem with multiplication in the numerator, multiplication in the denominator. There's no addition and subtraction. We've taken care of the factorial symbol. So now we can actually just do some canceling to make this a little bit easier. So all of this, 7, 6, 5, 4, 3, 2, 1, can be canceled with this up here. And so now we just end up with 10 times 9, which gives us 90, and then 9 times 8, which gives us 720. And it makes it a little bit easier. And now the last situation is when we have permutations that are going to allow for repeatable events. Okay. So for example, in the word math, we have 4 letters in the word math. If we were going to rearrange those letters and just take those 4 letters and rearrange them, we can find out how many rearrangements there can be. And so we're going to say we have 4 options for the first space. Okay, that first space we could have 4. And then when we move to the second space, right here, now we only have 3 letters left to choose from. Okay, remember, we're not necessarily spelling the word math, we are using M, A, T, and H to make different combinations. And then when we get to the second space, we've already used 2 of the letters, we only have 2 left, and then that last space leaves us with no options. Whatever's left over, whichever letter hasn't been used, has to go into that last spot. So then we'll put a 1 in that spot. So 4 times 3 times 2 times 1 is 4 factorial. So we can write that as 4 factorial. All right, and that actually comes out to be 24. Okay, if we have a situation like in number 27, here the letter L is repeated twice. So we have 4 spots. So in the numerator, we're going to have a 4 factorial. Okay, but now we need a new formula because now we have repeatable events. So the new formula, when you have items that are going to be repeating, the formula is n factorial. So the n stands for the same thing it stood for up here, total objects. But we have a new variable that we call s. And there's going to be s sub 1, there could be s sub 2, etc., etc., etc. What the s stands for is the number of objects repeated. So, for example, in this case, we have the L that is taking up 2 spots, so it's repeating twice. So our S in this case is going to be 2. So what we do is, and we only have 1 letter repeating, so we're only going to have an S1. We're going to write 2 factorial here. So 4 factorial, again, we found out for number 25, we don't even need to do it again, is 24. 2 factorial is just 2 itself, 2 times 1. And we end up with a total number of permutations of 12. All right, let's move to 31 because in that situation we actually have 2 letters repeating. So we have, if we count through the letters, we have 8 letters total, 8 spaces for letters. So that's going to be your 8 factorial in the numerator. And then we have the E's repeating as well as the A's repeating. So there are 2 E's, 2 spots for E. They're both going to repeat. So we're going to say 2 factorial. And then we're going to multiply that by the number of times the A repeats, which in this case is 2 as well. So I'm going to multiply that by 2 factorial. So I'm going to have 8 factorial in the numerator. And then in the bottom, now this is not 4 factorial, this is 2 factorial times 2 factorial. All right, so now we have all multiplication. What I can do is do some canceling just like I did up here in number 22. I can cancel these two, that 2 and 1 with this 2 and 1, and it'll make it easier to find that final answer, which when all said and done is 10,080.